This is June 2001, an old style question. It's question 7, and we're doing part B now. Part B, a stone is projected with a vertical component of velocity 30 metres per second from the edge of the top of a tower, and the tower is 200 metres high. It follows a trajectory as shown, so it goes upwards to a maximum height and then goes down again. It says calculate the time after projection at which the stone reaches its maximum height. So I might be able to do this on the page actually. I'll scale in a bit so you'll be able to see this a bit better. So what it does is it leaves the person's hand, goes to the top of the maximum height, and then it comes down again. So we need to find, really, it's a section here between here and here we need to find some information about. So we know it's projected with a velocity of 30. We know that it reaches its maximum height, its velocity is 0, and we know that A is equal to minus 9.81. I'll just scan in a bit so you can see this quite clearly. Okay, so we're looking for a maximum, we're looking for a time, and so V is equal to U plus AT, T is equal to V minus U over A, and that gives you then T is equal to V 0, U is 30, A is minus 9.81, and time comes out then to be 3.05 seconds. There's your answer there. Next part of the question, what is the maximum height reached above the ground? So the maximum height then is going to be just finding S. So if we can use any of our equations for this, we'll use S equals UT plus a half AT squared. And U is 30, T is 3.05. A is minus 9.81. And T is 3.05, and it's all squared. And when you do that calculation, S comes out to be 45.9 metres. But it asks you for the maximum height, and it's already been projected from a tower 200 metres high. So our total is going to be 245.9 metres is your answer there. 245.9 metres. Part 3, the total flight time until the stone reaches the ground. And I'm going to have to do this on a white page for you. So this is part B, part 3. There's 2 parts to the flight. This upward part and then the downward part, which is this part here. So we already know this time for the upward part. That time's 3.05 seconds. And we need to work out this downward part. So the downward part, we know it's starting with initial velocity of 0. We know A is 9.81, and we know the distance. The distance from the last question is 245.9 metres. And therefore, we'll find the time for this bit. So S equals UT plus a half AT squared. Uh, 245.9 is equal to, now U is 0, so that's first bit 0 plus a half, and it's minus 9.81. Sorry, it's falling, so it's plus 9.81, and then it's times T squared, which is, we don't know. That's what we're trying to find out. So when you do that calculation, the time there comes out to be 7.08 seconds, and therefore I'll just finish this off over here. The total time then is the 7.08 seconds, which we worked out from the downward fall of the ball, of the object, and then we have to add in our original 3.05 seconds, and the total time comes out to be 10.1 seconds is your answer there. Another stone is projected into the air from ground level at a velocity of 25 metres per second at an angle of 35 degrees to the horizontal. Calculate the horizontal range and then calculate the magnitude and direction of the velocity 0.6 seconds after projection. So if we look at this, and I'll draw it out here, this is part C and it's part 1. If we just draw out our projectile like that and draw a horizontal ground underneath it, you know that it's projected from here, and it's got two components, a vertical component and a horizontal component. So the first thing we need to find is its horizontal range. So we need its horizontal component. It's projected at an angle of 35 degrees and a speed of 25 metres per second. So our horizontal component, this is the line beside the angle, so therefore this is the one which involves cos. So that's V cos 35 degrees. Our vertical one then is V sine 35 degrees. So we need to use the horizontal, we're trying to find a horizontal range, but the problem is, if I write down what we know horizontally, we know that the initial velocity is V cos 35, but we don't know what time it takes, and we don't know what its distance is. That's what we're trying to work out. There's only one equation we use here, and that's velocity, which in this case is this u value. Velocity is distance over time. So that's the only equation that you actually use for the horizontal component. But we have two unknowns there. We can't do anything yet. So what we can do is find the vertical time, because obviously the time it takes vertically to move up to the top and then down again is exactly the same as the time it takes horizontally. So what do we know there? We know that u is V sine 35. We know when it lands down on the ground again that its final velocity is a negative value of that, minus V sine 35. We know that A is equal to minus 9.81, and we're looking for time, and then we're going to use the time in this equation. So u is V equals u plus AT. So we know V is 25 here, so I'm going to put in minus 25. The sine of 35 is equal to 25 sine of 35 minus 9.81 times t. So when you bring this over, this becomes minus 50. The sine of 35 is equal to 9.81 times t. Sorry, that's a plus in there, of course. That's a minus. And then whenever you divide across here, the two minuses cancel each other. Over 9.81. And t comes out then to be 2.92 seconds. Now, unfortunately, that's still not our answer. We now need to find the horizontal range. So we're looking for d out of v is equal to d over t. We now know v and t. So v horizontally, or the velocity horizontally, never changes, and it's 25, the cos of 35, multiply it by the time, 2.92, and that gives you your distance. And the distance comes out at 59.8 metres. And we'll just round that up to 60 metres. Now part 2 asks you to find the magnitude and the direction of the velocity 0.6 seconds after projection.